Alright, great kids, here's your lecture on oxidation numbers. In reality, this lecture is on redox reactions. That's oxidation reduction, redox reactions, a new type of chemical reaction. However, to get there, we have to understand these things called oxidation numbers. So let's read and see if this makes sense. Chemists have devised a set of arbitrary rules to assign charge to atoms for the purpose of accounting for the electron transfer in redox reactions. The oxidation number, or state, is the charge in which an atom appears to have when electrons are counted by those rules. Which rules? Well, these 8 rules shown here. 1, 2, 3, 4, 4, 5, 6, 7, 8. We use oxidation numbers to follow the transfer of electrons. When using oxidation numbers, the positive or negative sign precedes the numerical value. So, if I were talking about charge of calcium, it would be 2 plus, and the oxidation state of calcium would be plus 2. I don't care actually which way you do it. You'll notice that I always put my oxidation numbers up on top and my charge to the upper right-hand corner. That's how I do it. But the right way to do it is actually before the number, but that's fine either way. Let's look at these rules and then apply them and see if they make sense to us. An element, when not combined with atoms of a different element, has an oxidation state of 0, regardless of the formula. So, things by themselves count as 0. In monatomic ions, one atom, the oxidation number is equal to the charge of the ion. So, if I have an ionic compound with 2 monatomic ions, the charge would be the oxidation number. So, diving into this thing right here, that would be Ca2 plus and 2 Cl negatives, correct? So, the charge, there it is, turns into the oxidation number. No big deal. And then another example, iron in FeCl3 has an oxidation state of plus 3, because its charge would be 3 plus, while Fe in FeCl2 has an oxidation of 2 plus, because its charge would be 2 plus. All right, so that's how that works. All alkali metals, and if you remember, alkali metals are really things in group 1, have an oxidation state of plus 1. In alkali earth metals, that'd be group 2, have an oxidation state of plus 2. Cool. The halogens have an oxidation number of -1 in binary compounds with elements of a lower electronegativity. By this logic, fluorine in a binary compound always has a state of -1 because it is the most electronegative. The oxidation number of oxygen is -2, except in peroxides, and a peroxide is a polyatomic ion, there it is, where oxygen state is -1. An example of that would be this peroxide right here. An easy way to identify a peroxide is when you have a metal and a nonmetal, the nonmetal being oxygen. The metal, in this case, we know that sodium has a plus charge. If there were 2 of them, however, this formula doesn't make any sense, right? So if it was just Na plus and O2 negative, that should be Na2O, but I have another 2 there because this oxygen is actually peroxide, O2, 2 negative, which would change this Na plus needing 2 of them to cancel out your total overall charge. So it's kind of how you identify peroxides. Now, the other exception to that is when it's with fluorine. And when oxygen is with fluorine, it could either be +1 or +2, shown by these examples right here. Kind of neat. Oxidation number of hydrogen is +1, except in binary metallic hydrides. What is a binary metallic hydride? Well, a binary metallic hydride means binary 2 things. One is a metal and the other one is a hydrogen, shown here. In these cases, it's actually -1. And if we look at that a little bit closer, you can see that this would be -1 and -1 because calcium has a +2 charge here, and I need my overall oxidation number to equal 0. That'll make sense in a minute. Oh, here's that minute right here, number 7. In all compounds, the arithmetic sum of all oxidation numbers of all the atoms and compounds must equal 0. So when you add them all up, they equal 0. This is kind of like charge. The overall charge is also 0 in ionic compounds. If we look at this as an example, Na2SO4, we know that each sodium has an oxidation state of +1. There's 2 of them, so it's a total of +2. I know that sodium has an oxidation state of +1 because it's an alkali metal, therefore it's +1. The oxygen has a state of -2. I know that because it's always pretty much -2 unless it's in a weird case, for a total of -8 because there's 4 of them. So if we're doing the math here so far, we have +2, we have -8. The only element that's left there is sulfur, and therefore it must have an oxidation state of +6 in order for the sum to be 0. I only have 1 sulfur there, so that has to be +6. This would be -2, and this would be +1. Overall, my total oxidation state would be 0. The last rule is for polyatomic ions. For polyatomic ions, the oxidation numbers of all the atoms must add up to the charge of that ion. For example, I have ClO2 negative. That means everything added together must equal -1. If I do some math, the two oxygens contribute a total of -4. Each oxidation number would be -2, so for a total of -4 because there's 2 of them. That means the chlorine must have an oxidation state of +3 because +3 and -4 is -1, and that's the charge of the actual ion. In this case, you can see how rule number 4 does not apply because chlorine's electronegativity is 3 while oxygen is 3.5. If we look at rule number 4, the halogens have an oxidation number of -1. Well, chlorine's a halogen, but it's not -1 in this case because it's with oxygen, and oxygen is more electronegative. Let's rip through these practice problems and see if you guys can keep up. So, potassium's in group 1, that's a +1. Chlorine's in group 17, that's a -1. Those are its oxidation numbers, together they equal 0. KClO3, all right, so that's +1. This is going to be -2. There's 3 of them, that's a total of -6. And if I have +1 over here and -6, it means chlorine has to be +5. Bromine, let's get rid of this work. We'll get a smaller thing here. All right, bromine, who knows? Because it's with oxygen, oxygen is more electronegative, so oxygen is -2. I need an overall charge of -1, so that means bromine can only be +1 to have those charges kind of even out to a total of -1. Fe3PO4 parentheses 2. Wow, that's a lot. All right, we can do this iron first, believe it or not, because it's a monatomic ion. That means its charge would have to equal its oxidation number. Let's figure out its charge. So phosphate is PO4 3 negative. There's a total of 2 of those, so it's a total of 6 negative. And that means I need 6 positive over here. There's 3 of them. So that means my charge in this iron is going to be 2 positive, which means its oxidation is +2. Let's get rid of that and keep on running. Now, over here, we have a whole bunch of things. Let's figure it all out. Oxygen is -2. If oxygen is -2, there's 4 of them. That's a total of -8 times 2, which equals -16. So now that I have -16, I have a total of +6. What does this phosphorus need to contribute? It needs to contribute +10. There are, once again, 2 of them, so each one is +5. That was pretty crafty work by me, if I must say so myself. Our next one looks like we have a charge, meaning a polyatomic ion. So overall, I have to have a -1 charge. I know that hydrogen is going to be +1, oxygen is -2. There's 3 of them. That's a total of -6. And if we have +1 and -6, this should be +5. But guess what? I need a -1 charge, so it's only going to be +4. Not too shabby. Next one. Okay, chromium, who knows? Oxygen is going to be -2. There's a total of 3 of them. That's -6. So I need +6. There's 2 of them, so this is going to be +3. Our next one, sodium. All right, that's a group 1 metal. Group 1 metals are going to be +1. There's a total of 2 of them. That's +2. Whoops. And then we have oxygen. There's going to be -2, so that's a total of -6. And the difference between those two, to make it sum to 0, would be a +4. That means each individual sulfur has to be +2. Not too bad. All right. Now, MnO2. Ooh. Okay, so this is a metal and O2. So if this is a peroxide, meaning it's O2 2 negative, that is the case in which oxygen, its oxidation state would be -1. There's 2 of them, so that's a total of -2. So manganese here would be +2. So that's one option. However, you don't know if this is a peroxide or not because manganese can have a different charge. It doesn't necessarily have to be +2 in this case. So I could call this a non-peroxide. If it was a non-peroxide, MnO2, each oxygen would be -2, so a total of -4, meaning manganese would be a +4. In this case, either option would be correct. You could give me either answer, doesn't matter. Calcium carbonate, all right, so calcium is going to be +2. That would be its charge. It's an alkaline earth metal. Oxygen's a -2, so that's a total of -6. We have +2. The difference in that carbon is going to have to be +4 in order to have everything equal to 0. All right, let's do this monatomic ion here first. Whoa, drifting away. If I do nickel first, I'd have to figure out its charge. Nitrate is -1. There's 2 of them, so that's a total of 2 negative in terms of a charge. So my charge would be +2, meaning my oxidation state would be +2. All right, let's do the rest of this now. So oxygen, -2. There's 3 of them, so that's -6 times 2, that's -12. If I have -12 and +2, nitrogen is going to have to contribute a +10 charge. There's 2 of them, so each one's going to be +5. H2SO4, all right, hydrogens are going to be +1, that's a total of +2. Sulfur is going to be -2, there's 4 of them, it's total -8. That means this sulfur is going to have to contribute 6. There's only 1 of them, so it's +6. Our next one, ooh, this one looks scary. So potassium's in group 1, so that's +1, a total of +2. Oxygen, that's -2, and there's a total of 7 of them. Whoa, drifting away. The total of -14. All right, that means this chromium has to contribute a total of +12. There's 2 of them, so each one's going to be +6. That was a rundown on how to do oxidation numbers. Now, let's see if they make sense when we actually apply them. So, in chemistry, I taught you synthesis, decomposition, single replacement, and combustion. Believe it or not, these are all redox reactions. All right, so these are all, that's too thin. These are all redox. And what I mean by that is they all actually have a transfer of electrons. We're going to assign oxidation numbers and then show you how these are all redox by following the actual movement of the electron. So for oxidation numbers, let's do green. Why not? It looks kind of fun. 0, 0. Those are individual elements, so their oxidation numbers are 0. Bromines, group 17. It's going to be -1. There's 2 of them, so copper has to be a +2. I mean, copper started at 0 and went to a +2, and bromine started at 0 and went to a -1. All right, so how do you go from 0 and end up at +2? Do I have to lose negative things or gain negative things? This would be the loss of electrons. And bromine, that would be the gain of electrons. And go from 0 to -1, I would have to gain that electron that was lost by copper. In redox, there's a simple way that we're going to figure this all out. And the way that we're going to do that is Leo the lion says grr. That is how we're going to figure out which one's oxidized and which one's reduced. Loss of electron is oxidized. Loss electron oxidized. Gain electron reduced. Gain electron reduced. There's a bunch of them out there. This is a great way to figure out which one's oxidized and which one's reduced. In this case, copper loses electrons, so I know it's oxidized. Bromine gains electrons, therefore it is reduced. I like this method specifically because it has that electron in there to make sure you remember we're following electrons. Another one that's popular is oil rig. I'll use a different color, maybe red. Oil rig. Oil rig is oxidation is loss and reduction is gain. That's fine, that works, but it doesn't mention the electron in there, which is why I like Leo Gur better. The final way you can kind of memorize these things is you're reducing your number. And when you're reducing your number, you are reduced. Meaning, if your oxidation number is reduced, 0 to -1, that is reduction. That's the whole idea. The other one is the opposite. You're increasing your oxidation number, therefore it is oxidized. So 3 different ways to identify if you're being oxidized or reduced. And all we're doing is we're transferring electrons, right? So in this case, the copper is losing electrons and bromine is gaining the electron. And that's what happens with synthesis reactions. It's actually the transfer of electrons. Let's look at decomposition. First, we need to assign our oxidation numbers. We'll do the same color code we did before in green. So it looks like these are 2 zeros, nice and easy. Oxygen is -2, hydrogen is +1. That means hydrogen goes from +1 to 0, and oxygen goes from -2 to 0. So how do you go from +1 to 0? Do you have to gain electrons or do you have to lose electrons? If you have a positive charge and you gain a negative thing, 1 electron, so if you gain electrons, Therefore, your overall charge would be 0. For oxygen, if you go from -2 and you lose those electrons, you would then have a neutral charge. All right, so here you have more electrons than you need, you lose them, you end up with a neutral charge. Let's think about it in terms of Leo and Gur. Leo the lion says Gur. So loss of electrons, oxidized. This one's losing electrons, therefore is oxidized. And gain of electrons reduced, this one's reduced. Not bad. So in this case, we have, once again, the transfer of electrons. And this time, the oxygen is losing electrons, and the hydrogen is gaining those electrons. That's what decomposition looks like. It's actually redox. Single replacement. All right, I think we used green. Let's do some oxidation numbers. These two are nice and easy, 0 and 0. Sulfur is going to be -2, copper is going to be +2, sulfur is going to be -2, hydrogen is going to be +1. Now, let's take a look at sulfur to start. -2, -2. -2 to -2. Its oxidation number doesn't change. Therefore, it's not involved in that transfer of electrons. In fact, you guys should remember that sulfur in this case would be a spectator ion. It's not really involved in the chemical reaction. That's what we said before, because it's not either taking or losing electrons. No change there. The other things, copper goes from +2 to 0, and hydrogen goes from 0 to +1. All right, so how do you go from 0 to +1? You'd have to lose something negative, lose an electron. And how do you go from +2 to 0? If you have a positive charge and you gain negative things, you would have an overall charge of 0. All right, so we have gain and loss of electrons. We have the transfer of electrons, Leo Gur, loss of electron oxidized, loss of electron, that's oxidation. Gain of electrons reduced, that's reduction. So once again, we have the transfer of electrons. This time, hydrogen is losing the electron and copper is gaining that electron. That's how it works. Sulfur, not involved in the redox reaction. It's a spectator. Our last example is, once again, we were going to say it. This is, once again, redox. Single replacement is actually redox. It's a better term for it because it's the movement of electrons. Combustion, okay, this is the last one we're going to cover, so it's probably the last redox reaction. This is going to be a 0 here. All right, in this case, hydrogen is a +1 because here, well, it just is a +1, meaning carbon is -4. All right, there's 4 of them, that's total +4, carbon's -4. Here, oxygen's a -2, that's total -4, so carbon is +4. And over here, oxygen is -2 and hydrogen is +1. So let's take a look. My carbons go from -4 to +4. My hydrogens go from +1 to +1, and my oxygen goes from 0 to -2. There are 2 different locations. Both of them go to -2 in this case. We should realize that nothing's happening with this hydrogen. That's not involved in redox or the transfer of electrons, so we don't have to worry about that guy. Now we have to figure out, well, how do I go from, my -4 to +4? So if I had a negative charge and I lost electrons, or I lose electrons, I would then have a positive charge. And down here, if I have a 0 charge, well, let's keep the color coordination better. If I have a 0 charge and I now have a negative charge, that would mean I would have to gain electrons. All right, so once again, Leo and Gur, loss of electrons, this is oxidation. Gain of electrons, this is reduction. Okay, this is all happening kind of simultaneously. So a redox reaction is 2 things, right? You have one thing that's losing electrons and one thing that's gaining electrons. And that's what makes it together a redox reaction, or oxidation and reduction. That is your lecture today. Hopefully you enjoyed it.